Hello everyone. In this video we're going to talk about linear regression analysis in R. So for an outline, first I'm going to give a little bit of motivation about why you would ever use linear regression. What is linear regression? Why would you use it? And then we'll talk about simple linear regression, which is, as the name suggests, the most simple type of linear model. And first we'll take it from a mathematical viewpoint, because really underneath it's really just a mathematical problem. And then we'll add in some of the statistical view of the simple linear regression model, and then we'll talk at the end about some other considerations. Okay, this is not meant to be a full coverage of linear regression in R. This is like just the tip of the iceberg. This is just to get our feet wet, so to speak, in doing an actual model. We'll cover this again if you're taking data science 2. If you're in stats 2, you know a lot about linear regression, and this should be all review. If you're not, that's okay. But I wanted to make sure that I do at least something for the people who don't move on in this course to the second course. So if you don't move on to data science 2, I wanted to do something here to show you what actually modeling was, or what the heck I'm talking about when I talk about modeling. So as a motivation, we'll look at this scatter plot. I have two variables, x and y, and I plotted them here as a scatter plot. Okay, and so the question I'm going to ask is, how do I model the relationship between the x variable and the y variable? And when you look at it, you should say, well, you could say many things, of course, but the simplest thought that you have is, well, it looks kind of linear. The relationship looks linear. As x increases, then y increases, and so that's what we're going to do in this video. But as I talked before in sort of the modeling intro video, we really have two different things that we're interested in. One is inference, and so if I was asking a sort of inferential question, or what a statistician might be interested in if he's looking at the variables x and y, is how can I describe the relationship between x and y? And of course I can describe it with a line, but really I want to describe how x affects y in sort of a statistical way. And so we won't spend a lot of time on that here, because you should have spent a lot of time in that in stats 2. The thing that we are going to be more interested in, or at least at the end when you do linear regression, most likely as a data scientist, you'd be interested in how can I accurately predict y given some new value of x. So that's the prediction half. The other inference half we'll touch on here, but sort of move past, because I assume that you have it in a past class. Okay, so the simplest choice is a line. Okay, so I can fit a line to this data. The process of using a line to model the data, this data is generally called linear regression. Now, I put line/plane there because if I have three or more variables, three variables I can show in a three-dimensional graphic, but higher than 3 dimensions is very hard to show. And a line is no longer a line anymore, it's a plane. So we won't really talk about the geometry involved in these problems, but we'll be using a plane rather than just a line to model this data. So that's a general statement that linear regression is using a plane to model the data. If that made no sense, that's fine. We'll just keep on moving. And when we only have one predictor and one response, like we do here, that's called simple linear regression. Okay, only one predictor and one response. We can have a bunch of predictors, okay, and that's going to be called multiple linear regression. And then we could even have multiple y's, and that's going to be called multivariate regression. We'll never get to that point. We will get to multiple regression. Okay, so simple linear regression. I'm going to go through with a sort of mathematical viewpoint of how do I fit a line to data. Okay, that's an important problem that you cover in middle school and high school and now in college, all over the place. Everyone's interested in fitting a line to data. That's not inherently a statistical problem, that's a mathematical problem. So, fitting a line of best fit, as most people call it, is really an optimization problem. So, some of you may have had experience with optimization problems, some may not, but I have something that I want to optimize, or that could be minimize or maximize a value. And so when you do that, that's usually in a calculus course or in a linear algebra course or in maybe a numerical methods course. But to fit a line to data, it is a optimization task that can be solved in the simple cases with calculus and in the general case, which we'll never get to, with linear algebra. So the problem is I want to fit a line to data, but I can fit any data, any line to that data. And so there are an infinite number of lines that I can fit to the data. And so I made this video here, not video, I made this graphic that shows a bunch of lines going through the data. Okay, I could choose lines that don't even go through the data, but I chose ones that either hit some data points in one way or another, and lots of colors. How do I pick the best line? So there are many lines there, and how do I pick the best, or maybe how do I describe the worst? So that's a problem that has multiple answers to. The one that there's of course one answer for what we're going to do, but there's other answers that lead to other types of regression, so on and so forth. So can I say which is best, and how do I define good or bad? What makes a good or bad line? Okay, and so if you think to yourself, we'd have a great class discussion about this, but if you think to yourself, now what makes a good or bad line, you'd probably think that the line looks to trend with the data in the right direction. So for instance, the blue line or the orange line and even the green line don't really go along with the trend of the data. So the blue line goes downwards, but it looks like there's an upward trend. As x gets larger, y gets larger. So blue line's no good. Yellow line is a vertical line, probably not very good. And then the green line, of course, is a flat line, and so it doesn't show any change in y as there's a change in x, so probably not good lines. And so you're down to the red one and the purple one. Both of those lines go with the data, but one goes better than the other. And so how do you define best? Okay, and so the answer to that, at least for linear regression problems, is I have to create some numerical value that tells me that. And so to start, we're going to define what's called a residual. And a residual is the difference between an actual value of y and then the predicted value of y, which is the line. Okay, so really what a residual is the vertical distance between an actual point in your set of data points and the predicted line at the same x value. So the vertical distance between the point and the line, that's a residual. And so that gives us at least some measure of good or badness, goodness or badness, for how to choose which line is best. And so I could create a residual for each data point. And the question is, what do I do with those residuals? Do I add them up? Do I do something else? And so if you were in my statistics course, we talked about this, Stats 1, and you probably talked about this in your Stats 1 or equivalent class. You could add them all together, but it turns out you've got some positives and some negatives. And so when you add them, that could possibly cancel out. or that will cancel out. The goods and the bads will sort of cancel out, and you get a number that isn't representative of how good or bad the line is. And so what you want to do is you want to square those residuals and then sum them up. So here's a formal-ish statement. I define the error. Okay, it's the residual of the ith point, and then I define the prediction there. Okay, so I have a line, y equals beta naught plus beta 1x, where beta naught is the y-intercept and beta 1 is the slope. Okay, and so I don't know what they are, and so I'm going to estimate them using the data somehow, which we haven't found that out how yet, but we're going to do it somehow. And then when I make those estimates, when I estimate them from the data, they get a hat. In statistics, anything that's estimated gets a hat because it's a predicted value. All predicted values gets hats on them. And so that's how I define y hat is beta naught hat plus beta 1 hat x. Okay. So y hat sub I is the prediction of the ith value of x. So then I define what we're really interested in, which is what I'm going to call a residual sum of squares, RSS. You could also think of it as the sum of squared residuals. I think that's how I referred to it in my Stats 1 class, but here we'll switch around the letters, residual sum of squares. And so I square the residuals and I sum them together as the definition and the name state. Okay, and so I have that residual sum of squares, and my task, the optimization task, is to minimize those residual sum of squares. And so what I can do is take this definition of residual sum of squares and the material above and rewrite the residual sum of squares in terms of beta naught hat and beta 1 hat. And so now I have an equation with some unknowns in it, beta naught hat and beta 1 hat. So I'm going to have to take some partial derivatives and solve some stuff that we aren't interested in how to do. But when I do that with some calculus, I can actually get what are called closed form estimates of beta 1 hat and beta naught hat. Okay? And so you'll notice x sub i's and y sub i's. Those are the x and y values of the ith point. And then, of course, x bar and y bar are the mean of the x's and the mean of the y's. And so when you do all that calculus, this is what sort of pops out of the formula. Okay, so great. There are closed form estimates, and we can find that line. And so if that sort of wasn't clear through the calculus, which it may not have been, here is a visual that I've taken from ISLR that I think visualizes or kind of shows what's happening on the optimization side. So on the left-hand side, you've got a sort of a density plot. So that's not I forget what it's called at the moment, but it's like a density, sort of a 3D, it's called a contour plot. There you go. I remember now, it's called a contour plot. You can often see these in two-dimensional visualizations of mountains and such things. They can make contour plots and show you differences in elevations by how close those contours are. And then on the right is a 3D visualization, which I think is much easier to look at than the left one. And so you'll see they've plotted beta naught and beta 1 there for a specific example. You can see the three-dimensional curve there, the three-dimensional plane. And you can search through that plane and find the bottom point, which is our estimates. Okay. So now to the actual part that we're interested in. How do you do linear regression in R? Okay, because linear regression in R makes it very easy to do linear regression. You don't need to know any of that stuff that I just talked about to do it. R uses a powerful formula syntax to describe the model, and so it's going to look a little weird, probably, to you, but I'll describe it in full. So here's an example. I have some simulated data, and so I've done this before in our stats primer video, and so I won't describe the code, but there's the code, and there's the resulting table after I ggplot the data. Okay, so I've generated this data to have a linear relationship, but it's completely made up data. There's no meaning to x and y. Okay, but I have this relationship that y is equal to 3x plus 5. Okay, and so what I'm hoping sort of that the linear regression will do is calculate those true values. So essentially here I've had a line through this data. In general, I've generated the data from that line with some error related to it, or error involved in how it's plotted, and then I'm hoping to, what I'm going to refer to as, recover that line. And so here is the syntax for doing a linear model in R. The function that we're going to use is lm, okay, and then the first argument of lm is going to be a formula syntax, okay? And so you'll notice that it says y tilde x. Now before, we know the tilde from our per anonymous functions or lambda expressions, whichever you prefer they be called, okay? This is not a anonymous function here, okay? This is something different. It creates a formula, whatever that means, and then you feed it the data, and out pops an estimate of the slope and the y-intercept, okay? So it says that it thinks from the data, it calculated using the method we described before, calculated the slope to be 2.97, which is darn close to 3, and the intercept is 5.55, which is also pretty close to the intercept of 5. Okay, so this has done a good job at recovering that true line that we generated the data from. So that's how easy it is to do the fitting in R. So let's break down the syntax because it is a little confusing. So there it is again. The LM function stands for linear model, and so you might be a little confused, and you said, well, I thought we were doing linear regression. What is a linear model? Well, linear regression is a model that falls into a bunch of different models where the predictors are all a linear combination of one another. Okay, so that means on the right hand side, I have y equals some things that are added together that have x involved. Okay, so it doesn't have to be like x1 plus x2 plus x3. It can be x1 squared plus x2 squared plus x3. Okay, I could have squared terms involved. I could have all different kinds of terms involved, but as long as I add them together, that's called a linear model. Okay, so that's the LM function and why it's called that. The important part is the formula syntax. Okay, and so the formula syntax is y tilde x for this problem, and so it's read as y tilde x. The thing to the left of the tilde is the response, and then there could be a bunch of stuff to the right, which are the predictors in some form. Okay, and so there are a lot of different models that you can do, and you can describe them all with this formula syntax. Okay. All right, and then of course the data. So now, up to that point, it's all been completely a mathematical issue, but in this class, in data science, we are going to approach these things from a statistical viewpoint. Okay, so you have to indulge me because this is my life. You have to indulge a little bit of statistics. So the only point at which statistics becomes involved in such a problem is when the error term shows up. And so you remember this from the modeling video in the past, what we're trying to do, what we're sort of assuming all along in all of our problems that will come up, is that I have the predictors x and I have the response y, and there's some relationship f between them. And then there's going to be some stuff that we don't know that doesn't quite involve x or y. It just exists for some other reason. And we're going to call that, all that extra stuff out there, we're going to call error. Okay? And that error we'll call epsilon. And so the linear model is sort of the most simplest, or the most simple form of f, where f is just you add the predictors together. And in this case that we're working with now, we only have one predictor, and then we have this intercept term there as well. So f is just the, some people would call it the identity function. It just sort of goes away. So I have y equals beta naught plus beta 1x plus epsilon. So this is the theory of linear regression. And so this might seem ultra weird to you. It might make no sense, and that's okay. Just stick with me for this a little bit. So in theory, there's some true relationship out there between x and y in the population. So in truth, whatever x is when whatever y is, weight and height, okay, or whatever, you're assuming in some true world that x and y have a linear relationship with one another. Now, that's certainly not true in almost any case that you work with, but it is an assumption that's there in the theory of linear regression. And so you kind of have to go with it. It's crazy. Just stick with me. When we actually observe the data from that true relationship, we observe it with error. And so that error could result from a number of different reasons. Maybe how we're calculating, maybe how we're measuring x and y, x is not measured with error. X is true, but when we measure y, because it's the response, there could be some error involved. So maybe our instruments don't have enough accuracy to get the right value, or there could be a number of external factors going on. All of that is placed in the error, okay, the error epsilon. And so what we're trying to do with linear regression is we're trying to recover that true relationship with the least squares line. And so when we minimize the residual sum of squares, we're doing a least squares approach. And so the line that does that is called the least squares line commonly. And so then we have that least squares line. The only thing that's different from the mathematical to statistical view is that epsilon, and then the sample version of that is the e. Okay. So this is a view of the statistics of the line with a sort of statistical bend to it, and this probably looks really weird, but the line is really a line of averages, and it's meant to estimate the mean of y over different times of x. And so really we have this true line that exists, beta naught plus beta 1x, okay? And then the points really come from a normal distribution. A normal distribution, each with its own mean, okay, different means over time, but with the same variance. So what we have theoretically is this line with a bunch of normal distributions overlaid at each point. And so in truth, the data should come from the line, but there's some error involved, and the error follows a normal distribution. I know that's probably really weird to think about it. It's okay if you don't understand it. Your life can go on. So in addition to that theory of linear regression that goes on, there are actually a number of other assumptions that you need to meet. And so these are things that you've talked hopefully about in Stats 2, if you're in it now, or you have in the past, or you will whenever you take Stats 2, or if you're done with this class after it, you'll never see this again, and it's okay if you forget it. But there are 4 assumptions to linear regression. One is that the responses, and really this talks about the errors come from a normal distribution, each with different means, and then a common variance. Number 2, so that has to do with the errors involved. Step 2 is the mean of y is actually a linear function of the predictors, and so that's sort of easy to assume in the way we set up our problem, that y was a linear function of the predictors. The third one is called the variance is independent of the predictors. There's a common one and it doesn't change over time, and that's called homogeneity of variance. So that if the errors are homogeneous, they're the same, and if they're heterogeneous, they're different. So step 3 is called homogeneity of variance. And then the fourth is that the responses themselves are independent. Okay, and so there's no dependence involved. Now, again, that's okay. If you don't know this, this is just something I feel the need to talk about from my training. Okay, so that doesn't even begin to scratch the surface on linear regression. And again, we're going to go over this in detail in the second data science course, and so it's okay if you don't get it now. There's a lot of stuff we don't know, but let's get to the fun stuff, which is, well, you probably don't enjoy it. You don't think it's fun, but I do. Hypothesis tests and other stuff for linear regression. So inference about linear regression. We fit the data mathematically. What's the statistics involved? And so there's the same call that I had last time. I call it whatever comes out of the function fit. Okay? And so when I run the summary function on fit, it doesn't give me the 5-number summary. It gives me a bunch of stuff. And all of this you would talk about in a statistics course. Okay? What we're interested in, if you were interested in hypothesis tests, is you'd be looking at the probability of greater than the absolute value of t. That's a p-value, and so it gives you all these estimated stuff. So you'll see the numbers that were actually estimated are there, and then the p-values are important for hypothesis tests. Okay, and there's lots of good information there. There are actually graphical ways to check those 4 assumptions that I talked about, and they are here. Okay, and unfortunately, I've used a base plot, which makes me sick to my stomach, but I had to do it. Okay, and then lastly, what we'd be interested really in is a prediction. So if I want to predict values using that line, I don't have to write it out by hand, meaning I don't have to take the slope and the y-intercept and then use my own calculator. I can use the predict function. And so here I predict on 2 new values of x using the fit that I found. Okay, so that's where I'll stop for linear regression. Thanks for sticking around. I know it was a long video as always, but hopefully you gained something from here and maybe you can use for our final project. Okay, see ya.